Thank you for the opportunity to be here, and thank you for very many helpful actions from the committee, which has made my visit so excellent. This is a story from a long time ago, before most of you were born, more than 50 years ago. I was a graduate student at the time. I will give you a little bit of my background before I became a graduate student and then tell the story. So we start with my background. Yes, and if I do not talk too long, I will also tell you some other stories, because every so often when I go to a conference, somebody says to me, "You know, I nearly discovered pulsars," and tells me the story. And those stories are also very good. So if I keep to time, I will tell you some of those stories as well. I started life in Ireland, in the north of Ireland. And I started my academic career by failing an important exam at age 11. However, it had always been planned that I would go away to school in England, to a boarding school where you live at the school. And so my parents were anxious that I had good preparation for that. So although I failed that exam, I moved to the next level of schooling. In the first week of the first term in that upper school, a message for the first year class. This afternoon, boys to that building, girls there. I think this is sport. That's why they are separating us. It was not sport. The boys went to the science laboratory, the girls went to the cookery room. No discussion, no choice. When I told my parents that night, they went shoo and telephoned the head teacher. The local doctor had a daughter in the same class. He telephoned the head teacher. And the next time the science class met over there, all the boys and 3 girls. We were the first girls to do science in that school. We did physics the first term. I loved it. It was easy. In the exam at the end, I had 97%. The thing I got wrong was the speed of light. Question: what is the speed of light? And I write down 186,000 miles per second. Old British units, but the right answer. Then for the first time in my life, I look at that answer. That's very big. And change miles per second to miles per hour. It is a good idea to look at your answer, always. Just not for the first time in the exam. So that's Don't say this has stopped working. No, it hasn't. So that was my school in Northern Ireland. This was the school in England where I went to next at age 13. A boarding school. We live there. My home is hundreds of kilometers away. And I specialize in maths and physics. It was a girls' school, and girls' schools had trouble getting good science teachers. Our maths teacher was good. He taught at the boys' school. Then at 5 o'clock at night came to the girls' school to teach us. Our physics teacher was very old, but a very good teacher. Our chemistry teacher, we looked at the periodic table, we, the girls, and said, why is the periodic table that shape? What does it mean? He did not understand the periodic table. He said, God made it so. I go to university, to the University of Glasgow, to do a degree in physics. We have to do some mathematics, well, a lot of mathematics, some chemistry. I also did some geology. Great. I came top of the class without trying. Maybe I don't want to be an astronomer. Maybe I want to be a geologist. I go to see the professor. He says, no, not for women. So, okay, I'll be an astronomer. Back to physics. I ended up being the only female in a class of 50 for the last 2 honours years. And it was the tradition in Glasgow that when a woman entered the lecture theatre, all the men went. 49 men doing that when you come into the lecture theatre. If you blush, they make much more noise. Ladies, you can control your blushing. It takes a bit of practice, but you can do it. And I had to learn quite quickly how to do it. In my final year, I had as a tutor a curious little man called Ron Drever. Some of you may know the name. He was very clever, doing interesting things, and I made a note to watch whatever field Ron Drever worked in. Quite soon afterwards, he started working in gravitational radiation, detectors for gravitational radiation. And so I have watched that field from the very early days. I knew they would someday make a detection. I was not sure I would still be alive when they made the detection, but yippee! We now have gravitational waves. I had hoped to go to the Jodrell Bank, which is a big radio astronomy observatory. I had worked there one summer and thought, yes, I would like to do radio astronomy. Put in an application. No answer. I had been told they would not take women. Maybe that is their way of not taking women. Just don't answer. I will never get into Cambridge. I will have to go to Australia, to Sydney, Australia. But in Australia, the academic year starts January, February, not September, October. I have some months gap. I will put in an application to Cambridge just in case, but I'm not clever enough. I will not get into Cambridge. I get into Cambridge. Yes, yes. Perhaps some of you heard a bit about one of our prime ministers, Boris Johnson. Boris Johnson was a student in Cambridge, a little bit after me, but typical of the Cambridge student. Rules do not apply to me. I am brilliant. I do not need to do the work. I can spend my time with my friends drinking and talking, and everything will be okay. Many Cambridge students were like that. They believe they are infinitely bright. They will get a splendid Cambridge degree without any work. and I come to Cambridge, I'm really an outsider. This is the British Isles. I start life in Northern Ireland. I have some of my school here. I go to Glasgow University to do my degree. You see, this is the kind of mountainous, wild country, heathen country. And then I find myself here. Maybe Spain is more equal, but in Britain we have a gradient. And I came from the wrong side, of course. So I turn up in Cambridge and oh, they are all terribly clever. I'm not clever enough. They have made a mistake. They will throw me out. But I am not walking out. I will wait till they throw me out. And until then, I will work my very hardest, do my very best work, so that when they throw me out, I will know I have done my best and I am just not good enough for Cambridge. So I'm working very, very hard. If you go on to do a PhD, maybe when you start your PhD, you'll be given some tools or a computer or something like that. These are my tools. These are not microelectronics tools. These are full-size, man-size tools. Because I spend the first 2 years helping build a radio telescope. It involves working outside, summer and winter. It involves some quite heavy hammering and a lot of work with the tools that I was given. This is near the end of the construction. This is me. This is Don, my technician. And here we have some very special cable, low loss cable, which you cannot roll up and take indoors. So in the winter in Cambridge, I work in this little hut and that little hut, putting plugs on the ends of the cables. And now we are checking the plugs. We were building a very big radio telescope. 2,000 antennae, 1,000, more than 1,000 wooden posts, almost 200 kilometers of wire and cable in that radio telescope. And it's an area of 57 tennis courts. It's huge. It took 6 of us about 2 years to build. This is the finished article. This is actually a radio telescope. It looks like some kind of agricultural frame, but there are antennae. There's one lot along here just coming into view. There's another lot along there. A lot of copper wire. You see the copper has oxidized and is the nice blue-green color. And the wooden posts are to keep everything above the wet grass, because wet grass would be an electrical short. So you keep it up above the wet grass. For those who want a bit more detail, it worked as an interferometer. The two halves are separate, and we could make the beam go down or up by putting in delay cables. Transistors were just coming in, but Cambridge did not trust transistors. Oh, noisy things, unreliable things. We use vacuum tubes. So we had a lot of these vacuum tubes. They have one advantage. If your equipment is misbehaving, what you do is, and that makes all the valves go chuck, and sit down properly. And it works. You can't do that with transistors. Now, at this time, the objects that we call quasars had been very recently discovered, and in Caltech, Martin Schmidt and Jesse Greenstein had optical spectra of 2 of these quasars. And Martin cannot make sense of this spectrum. There are nice emission lines, but what element? It doesn't make sense. It looks a bit like hydrogen, but it's way at the red end of the spectrum. Aha, he thinks. Could it be hydrogen with a large redshift? He goes along the corridor to where Jesse is working. Jesse has a spectrum of another quasar, and he too has problems with it. He thinks tellurium is the nearest chemical element. So he's trying to write a paper explaining why these objects are full of tellurium, to give him a tellurium-like spectrum. And Martin comes in and says, Jesse, could it be hydrogen with a large redshift? And Jesse tries it. But it's too big a redshift. Redshift means distance. And these are very distant, much further away than anything else we've seen before. This is crazy. It's crazy, or maybe it is right and record-breaking. So they finally write up these spectra as hydrogen with a large redshift, and the world suddenly realizes that these quasars are very bright and very distant. But at the time I start work, there are only about 20 of them known, and we need more. So my particular project was to find more quasars through studying their radio emission. I can say more about the details later if anybody really wants. Very simply, if you have a quasar, it's way up there somewhere. The radio wave comes down to the Earth, comes through the space between the sun and the planets, where there is the solar wind. Solar wind is a plasma. It is not perfectly uniform. There are patches with more electron density, patches with less electron density, more, less, and all blowing past. This acts like a diffraction grating. A diffraction grating that is moving between your source and your screen. So the diffraction pattern you get keeps changing as the screen moves past. And the signal you get is not steady, but jumps up and down. These are the diffraction maxima and minima. And look at the time scale. To get good signal to noise, you should integrate for a long time. To identify a quasar, you should integrate for a short time. Problem. Make your radio telescope enormous. 57 tennis courts in size. And you get enough signal. University of Cambridge at that time had one computer for the whole university. It had less memory than your laptop. And very few people could have time on it. And we couldn't. Our data came out on rolls of paper chart. There was about 30 meters of paper chart every day. And I ran the survey for 6 months. So I had 5.3 kilometers of paper chart. So I think I've probably said most of this. We're looking for quasars. We're looking for quasars that will fluctuate because of the fluctuating solar wind going past. And I observed for 6 months. And yep, I got the number of quasars up from 20 to 200, which that's okay. You get your PhD. But just occasionally, remember, I know I'm going to be thrown out. Remember, I'm not clever enough for Cambridge, and I'm being very, very thorough. Occasionally, there is 5 millimeters of signal that I cannot make sense of. And this is one of the first sightings of it. This is some low-level radio interference. And they look different. Here you can see space between the spikes. Here you can't. These spikes go up and down. These ones go up mainly. It looks different. What you have done in your head is Fourier analysis. You have said, what frequencies are present? Here you can see chart between the spikes, lower frequency, higher frequency. And you also ask in Fourier analysis what amplitudes are present. Here we have positive and negative amplitudes. Here we have mainly positive. But they look different. They are different. The first time I showed this to my supervisor, having seen the signal a few times, he said, "You stupid fool." Oh, what have I done now? You stupid fool. This all occupies 5 millimeters. We can't see what's going on. We need an enlargement. With chart technology, enlargement is easy. You run the paper faster under the pen and it all gets spread out, enlarged. But I can't leave the recorder running at that speed all the time. It will get through a whole roll of paper in 20 minutes. And guess who has to live at the observatory putting a fresh roll of paper in every 20 minutes? Next best idea. Graduate student goes out to the observatory at this time, switches to a faster chart speed, lets it run to about here, and switches back to normal. And I did that for several weeks, and I made high-speed recordings of receiver noise. The signal had disappeared. This, of course, is the graduate student's fault. I don't know if we have many graduate students here, but if your supervisor gets frustrated, it's the graduate student's fault, even if it isn't. So I did know from what work I'd already done that sometimes I could see this signal when I looked at this bit of sky, and sometimes I couldn't. But it was really quite worrying. And then finally one day I got it. The labeling has been added afterwards. These are 1 second time marks, and here's the signal. And look, pulse, 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 about 1 1/3 seconds apart. Then it goes quiet, there's a few pulses missing, and it comes back on beat. And there might be some here, maybe. Beat, 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 beat. It's keeping phase, whatever it is. The amplitude is big or small or 0, but it still keeps the beat. This label was added later. It stands for Little Green Men, and the 1 shows you that I found more than one. which was good. Little Green Men was a nickname. I did not expect it to be taken seriously, but the newspapers got hold of this. So could it be local interference? We had a lot of problems, for instance, with pirate radio stations. But this signal moves around the sky with the stars. It keeps to the 23-hour, 56-minute day that the stars keep to, the sidereal time. Right, well, Jocelyn has wired up the radio telescope wrong. It's some feature of a telescope that's not correctly wired. So very quietly we asked a colleague, a research student and his supervisor, who also had a radio telescope with its own receivers quite nearby. Please, could you do a little experiment for us? Could you look and see if your telescope and your receivers pick up this signal? And I remember that afternoon, the way the telescopes were orientated, my telescope saw the signal first, and it was pulsing nicely. Good signal. We go and stand by the chart recorder for this other telescope, Robin's telescope, and nothing happens. Tony, my supervisor, Paul, the Robin's supervisor, start walking down this very long laboratory. Now, what could it be that shows in your radio telescope and not ours? Do you think it could be? I'm trying to keep up behind. Robin stays by his pen recorder. Do you think, no, that, because that will, but what about, no, don't think that'll work. What about, here it is! It's a shriek from Robin. We had miscalculated by 5 minutes when this other radio telescope would see it. If we had miscalculated by 25 minutes, we would have all gone home and the story would be different. But now here is another separate radio telescope with its own receivers picking up this signal. It's not a fault with my equipment. It's something beyond both our radio telescopes. And it also became clear to us that this thing, whatever it was, gave quite short pulses with quite steep rise and fall. And it also was keeping the period very, very accurately. It was the same day after day after day. It was not getting tired. The steep pulses means it's small. The fact that it does not get tired means it's big. Great. To be more precise, the steep-sided pulses means it's small in size. The fact that it keeps the period means it has big energy reserves, probably big mass. A colleague managed to get a dispersion measurement. You've probably all seen dispersion in optics, the way a prism will give you the coloured rainbow. You can get similar effects in radio if your radio wave goes past some free electrons. If there are any geophysicists in the room, you may have heard of whistlers. I'll see if I can do one. A lightning stroke on the far side of the Earth produces a radio wave which comes round to us following magnetic field lines. So it makes a big loop. In following that loop, it goes past some electrons, and what started out as a multi-frequency burst arrives as, can't whistle, sorry, can't do it properly, it goes wheew. And this thing's going wheew. By how slowly or how fast it goes wheew. Does it go whew, or does it go wheew? If it goes fast, it's gone past few electrons. If it goes slowly, it's gone past many electrons. By looking at how slowly it comes down, you can estimate how many electrons it has met on its journey. And if you make a guess at the electron density in space, you can work out how far away it is. And the answer we got was about 200 light years. So it's in our galaxy, but it's way beyond the solar system. But we only have one of these, and that's very worrying. Jocelyn, keep observing, do your thesis work, and please keep making special measurements of that one object. And late one night, just before Christmas, at about 9:50 p.m., significant time because they lock the laboratory at 10 p.m. and graduate students do not have keys. You could be locked in or locked out. But I want to be locked out because next day we are going to my family, my fiancé and I, to tell them we're going to get married. So I kind of have to be there. So I can't be locked in, but it's 10:50, and I think I've found another one. The telescope will see it at midnight. I will go out to the telescope at midnight and see if I have found another of these sources. It's December the 20th. It's cold and icy. I ride a little motorbike, only 2 wheels. 2 wheels on ice, not good. But I get there. I wire up. And in comes another pulse, 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 pulse. Slightly different period, totally different part of the sky. We now have 2 of these. They're real. I go away for the Christmas break to my family. We make our announcement. Tony keeps the survey running, which means he puts fresh paper in the recorders and piles the paper charts he's taken off the recorder on my desk. I come back and there's a cone of charts waiting to be analysed. Tony's in a meeting, so I start doing some chart analysis. Working through this. Which one's that? It's not either. It's a third one. Wow! Okay, I'll just finish this piece of chart and then I'll go back and see if I've seen anything at this right ascension and declination on any of my previous charts. Move along. What? 2 of them? A meter apart? And that moment my advisor arrives. Tony, look at this. Oh, thank you for keeping the survey running while I was away. That was extremely kind of you, and I will do the chart analysis. Actually, I've already started. And look what How many more have you missed? Go back through all your old records. I did go back through all my old records. It helped me appreciate that actually I had occasionally seen these 2. Never at the same time, but I had occasionally seen them. And we got special observations of each of them. This one was pretty ordinary. This one had a period of 1/4 of a second. Not 1 1/4, just 1/4 of a second. It's much faster. It's going to drive the theories about what this thing is. It's very small if it's got a period of 1/4 of a second. So I ended up finding 4 of these, as well as doing the data analysis for my thesis. Tony said it was too late to change my thesis title. From what I now know of university systems, I think he was wrong. But as a graduate student, you believe your thesis advisor. It's too late to change your thesis, Jocelyn. You'll have to do it on the quasars. I did, but I put the pulsars in an appendix. And the thesis, well, the appendix has been quite widely read. We decided we would publish the first one first because we had most data on that. And shortly before we were ready to send the paper off, Martin Ryle, the head professor, phoned up the editor of Nature, basically saying, "Hold the press, we have something interesting for you." The way Cambridge professors behaved in those days. Nature did publish it very, very quickly, I will say. And the other three we published subsequently. Also, because we've got some good scientists here, Tony gave a colloquium in Cambridge just a few days before the paper appeared in Nature. Gave it a very titillating title, and every astronomer in Cambridge came. There were two possible explanations for this kind of behavior: something oscillating or something spinning with a beam. So you see pulse, pulse, pulse. Tony favored the oscillating one. The way you tell the difference is by getting this first derivative of the period, because something oscillating, as it ages, the amplitude gets smaller but the frequency gets higher. Whereas something spinning, wait a minute, I've got that the wrong way round. No, I haven't, I've got it the right way round. Something spinning, as it ages, gradually slows and stops. So, if the pulse period gets longer as it ages, it's something rotating. If it gets faster, it's something vibrating. We weren't able to measure the derivative at that stage, but Tony was favouring a white dwarf doing some kind of oscillation, launching shocks into the atmosphere which somehow generate regular pulses of radio emission. Shortly before the paper was on the first one on Nature was published, Tony gave a colloquium in Cambridge, gave it a very titillating title, and every astronomer in Cambridge came, including Fred Hoyle, who sat kind of in the front row. And Tony went through this and said he thought it probably was an oscillating white dwarf. And Fred Hoyle is the first to speak, and he says, "I don't think it's a white dwarf. I think it's a neutron star," which at that stage was totally unknown. Okay, some theoreticians had thought about them, but none had been seen. In 30 minutes, Fred Hoyle had digested all that new information and hit the right explanation. It's a rotating neutron star, not an oscillating white dwarf. It's a rotating, highly magnetized neutron star. The magnetism is important. And when the paper was published in Nature, the press got very interested, and they promptly assumed this was signals from outer space. And the fact I had nicknamed them Little Green Men didn't actually help in that respect. Now, this is 1968 or 1969, and the treatment of women was very different then. The press interviews took a standard form. They would ask Tony about the astrophysical significance of this discovery, and Tony would give it to them. And then they turned to me for what they called the human interest. How many boyfriends did I have? What were my bust, waist and hip measurements? Was my hair brunette or blonde? No science, all this physical body stuff. Because young women were seen as sex objects, and the male sex was dominant. So I had a pretty horrible time. Photographers were saying, "Would I undo some more buttons, please?" And this kind of thing. It was pretty awful. But it was great to be involved in that kind of event and science, even if the journalists were really rather horrible. One journalist came up with the name pulsar. We had sort of given some thought as to what we would call these things. I've now forgotten exactly what we had, but it was quite long. And he said, no, you want a short name. What about pulsar? So it was the science correspondent of a very conservative British newspaper that named these things. Now, I'm going to tell you some of the stories that have been told me by other astronomers who say they nearly discovered pulsars previous to our actual discovery. The first one goes way back to 1957. We're in Texas at the McDonald Observatory, and McDonald has specified that the observatory is open to the public one night every month. This is the open night. There's a night assistant, and there's a student called Elliot Moore from Chicago. He's just finished his bachelor's degree. He's working at the observatory for the summer. And people step up to the telescope and say, "Oh, wow, gee," or whatever they said in 1957, when you get sight of the Crab Nebula through a good telescope. A young woman steps up to the telescope and says, "That star's flashing." And the night assistant starts to explain about scintillation. And she stops them. She says, "No, I'm an airplane pilot. I have an airplane pilot's license. My job is to fly new aircraft from the manufacturer to the customer. I fly at night. There's not much to do in the cockpit at night. I know about the stars and scintillation. That star's flashing." Now, that star does flash at 30 hertz. It is a period of 33 milliseconds. 30 hertz is usually too fast for people to see, except for some young women. In Canada, the main power supply used to be at 30 hertz, and some young women could see all the lights flashing. And so we know that some people, especially young women, can see 30 hertz. So she insists that star's flashing. The night assistant kind of gives up and moves on to the next thing to look at. And Elliot Moore notes that nobody follows up. We now know that that curious star in the center of the Crab Nebula is the remains of the star that exploded in 1054 AD to give the nebula, and the remains are a neutron star, a highly magnetized neutron star, which these days is a pulsar with a period of 33 milliseconds. I suspect she had seen the optical flashes from the Crab pulsar, but nobody believed her and nobody followed up. Always follow up anomalies until you understand them. You might be onto something quite important. In 2007, Australian radio astronomers, there's now quite a lot of people doing pulsar work and quite a lot in Australia, those Australian pulsar astronomers get a very excited message from a not young man called Charles Chisler. He's about 80. He's from the USA. He'd served in the USA military. He'd been based in Alaska at the early warning station looking for Soviet missiles coming in. And when things were quiet, his boss would allow him to play around with the equipment. He played around with the receiving antenna and found a number of flashing things in the sky. He'd done an astronomy course at college and he knew about right ascension and declination. Bless that tutor. He made the best note he could of the right ascension and declination, and he's just found the Australian online list of pulsars, and several of his objects are in it, including the Crab pulsar. So he sent this email to the Australian radio astronomers, setting out what he'd found. The Australians spent quite a lot of time talking with him and actually believe he was genuine and that he had very, very likely found some pulsars with the early warning system in Alaska. But, you know, classified, would never be able to publish it. He was actually being very illegal in sharing, in taking away that information and sharing it with the Australians. So yes, he made notes of approximate location. 10 or 11 of them have been identified as pulsars, because he's discovered the online Australia Telescope National Facility Pulsar Catalogue. Possible that all of them were pulsars. The first he's discovered was in the Crab Nebula, 1967. He would have beaten us to the Crab Nebula if he'd been allowed to publish. So that was an interesting diversion. The last example involves a woman called Sue Simpkin. Sue was Canadian, was brought up in Canada. Sue knows that she could see the 30 Hertz Canadian light system flashing. She was one of those people who could see those high frequencies. She's now doing ultraviolet spectroscopy, and an eminent Dutch astronomer, Lo Vulture, asks her to take an ultraviolet spectrum of that funny star in the middle of the Crab Nebula. So she does. She says the spectrum is quite boring, but she could see something that she described as waves going out from it. Crab pulsar, 30 Hertz. Sue Simpkin can see 30 Hertz. She was probably seeing the Crab Nebula, the illumination of the Crab Nebula by the pulsar. Lou Vulture says no. But when the Crab pulsar was discovered, he was man enough to say to her, "You were probably right." For this last one, I'm not going to name the observers. They were always acutely embarrassed about this story. A group of them doing a survey of the radio sky at 408 megahertz. I think probably just the northern sky, but I'm not absolutely sure about that. And they're using the largest telescopes they can, and they get, 5 nights here and 7 nights there and 3 nights there. And they've just about finished mapping the whole of the northern sky, except there's 1 or 2 little squares that need filling in, and they're doing the filling in. It's before we used computers widely. They're using pen recorders. And one of the pen recorders tended to misbehave. It could be a bit sticky. The pen would kind of stick and then jump as it got unstuck. It's about 3 o'clock in the morning, very, very near the end of the real end of all their observing of this catalogue. And that sticking pen recorder starts going chuck, 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 chuck. And the observer says, "Oh, damn," and did what we always did to sticking pen recorders. And it stops going chuck, chuck. It goes back to normal. Turns out that he had actually been observing a pulsar. He did not put anything in the logbook. If he had made an entry in the logbook, they could have claimed prior discovery. But he didn't put anything in. And we now know that they were observing the very high latitude pulsar 0329 plus 54. So as I say, they were all very embarrassed about that, and the lead observer is no longer with us. He died a few years back. But yeah, there are some near misses in science. And it's probably you as a grad student who will have the time, and I hope the energy, not to cut corners and to follow things up, because you might find something quite important. I want to finish by paying tribute to Franco Puccini, an Italian astrophysicist, not an observer, a theoretician, but a very able one and a very nice man. The Crab Nebula was quite a problem. We know that the supernova was in 1054 AD. We know that the nebula ought to have faded by now, century or so, 2 centuries later. The Crab Nebula has not faded much. Why not? What's going on? And Franco came up with an idea which initially sounded quite wild, but actually has turned out to be the right answer. He says, suppose there's one of these funny things we call neutron stars, which none of us have ever seen, but never mind. Don't let that stop a theoretician. Imagine there's one of these neutron stars. it's going to be spinning quite fast because it's compact. Imagine it's got a strong magnetic field which is offset from the spin axis. So if that's the spin axis, the magnetic axis is like that. And as the star spins, the magnetic axis cones around and occasionally points at us. But that's by the way. As it spins around, it's going to emit magnetic dipole radiation. And if the electron density in the nebula is high enough, that magnetic dipole radiation will not escape. Its energy will be dumped in the nebula and keep it shining. And lo and behold, some years later, we find that in the Crab Nebula there is a pulsar, which is energizing the nebula itself, exactly as Franco predicted, and keeping the nebula shining. It was quite a complex line of argument he had to make, with some pretty advanced physics, but he was a remarkable astrophysicist. So finally, some factors that I think led to the discovery. We had our own telescope and our own receivers. And I made it my job to make sure that I understood all the foibles that there were in the telescope and the receivers. Because I'm a graduate student and I don't have any responsibilities for teaching, lecturing, things like that, I've got time to follow up anomalies. And remember, I'm scared about being thrown out of Cambridge. I am finding anomalies to follow up. So I'm chasing these things up. Until then, people had tended to use longer integration times because that improves the signal to noise. If you have a short integration time, you need to get more signal somehow, like a large collecting area. So you can say this is one of the first times this bit of phase space has been observed. We weren't aware of any other observers doing similar work, so we didn't think anybody else could have tripped over these things, so we didn't have to rush and panic to publish. We could take a little bit of time to be absolutely sure about what we were saying. And we had a good address. I think you probably agree that Cambridge University is a reasonable address. If you're going to find something really revolutionary, you need a good address. You need a place with a good reputation, or you may not get published, particularly if your result is too wacky. At that time in Britain, when you had funding from the Research Council, basically the government, to do research, you had to write reports on how you'd spent the money. Increasingly, when you apply for money, you have to say what your objectives are. And then when you report at the end, they're looking to see if you have ticked your objectives. This was not one of our objectives. It couldn't have been. Would we have been marked down for deviating from our original program? If we had computerized the search, since pulsars were undreamt of, would we have excluded that parameter space when we set up the computer search? Particularly because computers were few and far between. You didn't waste computer time. So we probably would not have found them if we'd computerized the search at that time. And I was working at lower frequencies than people had worked at for quite some time. They'd gone to higher frequencies for better angular resolution. So there probably weren't many people working at such low frequencies. And until quite recently, I would have said in radio astronomy, apart from the pulsar astronomers, the time domain has been neglected. But actually, now that we've got bigger telescopes and we're beginning to find things like fast radio bursts. The time domain is at last in radio astronomy being quite well researched. And if you want an area to go into, I'd recommend fast radio bursts. They're a bit like single pulsar pulses, but they're not. And I was working at a relatively low frequency. It's a frequency band, a frequency range that's been neglected actually for a long, long time. But at last, again, people are going back to it. So I'll stop there. I've detained you long enough. Thank you for your interest. Thank you for your attention. Thank you, organisers, for a great meeting. Thank you. Good.
Thank you very much, Jocelyn. We want to thank you for coming to this Congress. We all know that taking out time is very difficult sometimes, and today we are very grateful for that you are able to share this experience with us. So thank you very much. And now let's take a round of questions, if someone have any question.
Hi. So I wanted to ask you, how do you see the current picture of women in science? Because you've commented all along the presentation that you had difficulties, and I wanted to ask you that.
Yeah. There's no actually meetings for women in science because there's particularly women in astronomy. There's quite a lot of attention given to this now. In all the areas of physics, I think it's probably astrophysics that has the highest fraction of women, and it's improving all the time. I would not claim it's perfect, but it is certainly getting a lot better. And I think young women should expect to be able to work in the field equal with young men.
Thank you.
Anyone have another question? Okay.
Hello, and thank you again for the presentation. I would want to know about that part of the talk where you said you could take a little bit more about the quasars if we wanted to know about. Why not?
Okay. So the name quasar stands for quasi-stellar radio source. They were initially discovered as radio sources. They're some of the strongest radio sources in the sky. But now optical astronomers regularly observe them also. They are approximately galaxy mass. They contain a massive black hole at their centers and then material round the outside. They are sources that will sometimes flare and die away again. That's sometimes how they're noticed. But they're notable, I think, particularly for their massive black hole. Maybe 10 to the 8 solar masses black hole in the center. And because of that black hole and the strength of emission that they emit, we can see them at great distances.
Okay.
Hello. Firstly, I would like to thank you for a very inspiring talk. And I wanted to ask how, because you described when you were describing the beginning of your career in astrophysics, you worked a lot in instrumentation and all that. And I wanted to ask, like, how you think that enriched your career in astrophysics. And also any advice for, if you have any advice for people who are starting their careers in astrophysics and how to deal with imposter syndrome that you talked about and all that. Thank you.
So my career looks very different from a man's career. I got engaged to be married between discovering pulsars 2 and 3. And I was very proud of the engagement ring and wore it to work. Don't. Definitely don't, even today. Because you send a signal that you're leaving. You're not serious about astronomy, you're not serious about research. And that was even more true way back then. But because I got married, and married to a man who had to move his job to another part of the country every so often, and we had a child, I ended up being what we sometimes call the trailing spouse. And the way we would work it, my husband would say, there's a job going in such and such a place which I'm interested in. If we went there, is there any astronomy place anywhere near this? And if there was, he'd apply. If he got the job and we were moving there, I'd then write a begging letter to this astronomy place saying, might you have a part-time job, because we had a child by then, in astronomy, any kind of astronomy. So I moved from radio astronomy to gamma ray astronomy, to X-ray astronomy, to infrared and millimeter. And then I became head of a department myself and set up a group studying close galactic binary systems at any wavelength that was useful. But it's difficult, you know, it's difficult managing having children, it's difficult managing jobs for two partners in the same place. Whether it should always be the wife that plays second, I'm not sure. Over to you.
Okay. If someone is watching the Congress online, they can also make questions in the chat.
Many thanks for your nice talk. And I want to just to ask you why you didn't present the main pulsar that you is the only one object, because is as far as I know, you are the only scientist who received a $3 million prize, and you donate for science to promote the role of minorities on science.
Yes.
This is a untypical effect. So this is a new pulsar in science.
So, yes, there's this prize called the Breakthrough Prize, funded by a rich Russian who, for some reason, has gone to Earth. And he funds it for what he calls a breakthrough in physics. And mostly it goes for theoretical type physics breakthroughs. But one year it was awarded to me. And I thought, if people know that I have a prize of getting on for $3 million, my telephone is not going to stop ringing. I need to decide quick what to do with this. And I had a quick discussion with my son, who is also a physicist. Funny that, isn't it? And I said I was thinking of funding, maybe funding women, because quite a lot of my story hinges on the fact that I'm female, a minority, and working very hard to justify my place. And between us, we worked out that it would be good to fund some graduate students who were from minority backgrounds, hoping that they might appreciate the opportunity, really work very hard, and maybe discover something. So the money went to our professional body, the Institute of Physics. I phoned up the chief executive and said, would you like $2 million, $3 million? And he, you know, for blah, 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 blah. He said, yes, we were thinking of doing that anyway. Yes, please. So before the announcement, I already had a destination for the money, which saved me a lot of hassle. And the scheme has now funded 4 years, I think, typically 5 or 6 graduate students starting each time. They are mostly women, but there is, for instance, a very disabled young man who's also one of the recipients. So it's for any underrepresented in physics group.
Thank you very much.
Any more questions?
Thank you so much for coming. I wanted to ask if there's any consensus on what fast radio bursts are or their nature.
Yeah, fast radio bursts are fascinating. They're one of the hot topics at the moment. The quick answer is there isn't any consensus, but let me just tell other people a bit about what these things are. Pulsar radio astronomers are looking for pulses, and they're checking on the dispersion of the radio signal, because that ensures that it's from something with a lot of electrons between us and it, not somebody doing something in the next door laboratory where the dispersion would be 0. So they automatically check the dispersion. And these radio astronomers started picking up some single pulses with huge dispersion, way beyond our galaxy. And for the first one, they thought, well, it must be some crazy kind of interference. Then they started finding more. Then the Australians started finding a whole lot with the same dispersion. And when a grad student plotted that lot against local time, they tended to occur around midday, 1 p.m., lunchtime. A microwave oven has to turn icy material, warm it, melt the ice, and ideally turn the water to steam to heat the object. The frequency of ice water is slightly different from the frequency of liquid water, is slightly different from the frequency of steam. A microwave oven has to cover a range of frequencies. And typically, if we plot frequency against time, it scans down like this to cover, ice, water, steam. And when a graduate student plotted the occurrence of these things against local time and found they occurred at lunchtime, the astronomers suspected the microwave oven in the astronomer's guest house, which it was. If you open your microwave without stopping it, you get a short burst of microwaves, beautifully scanning down in frequency. And that explained some of the rather different bursts that the Australians were getting. Having set aside microwave interference, we now know there are these things called fast radio bursts, a few of which repeat, but a lot of them seem to be one-offs. They scan down in frequency simply because they've come past a number of electrons in space, and you can get an estimate of the distance, and they're way beyond our galaxy. Their position in some external galaxies has been broadly located, but not really sufficient to pin things down. They're towards the center of massive spiral galaxies. So fast radio bursts are currently one of the very hot topics in radio astronomy, and I think there's still no agreement as what producing them. They've also been useful, for example, for identifying some of the missing baryons in the universe. Did you know that we're lacking 3/4 of the baryons in the universe? We can't tell you where they are. Well, we can now because of the work with those fast radio bursts, which are from distant galaxies. And they're in the warm, hot intergalactic medium, which of course is very clear and exactly what you expected, isn't it? So, yeah, fast radio bursts, a very hot, sexy topic at the moment. Lots of question marks about what they are. totally unpredictable as to when they come about, of course, which is half the fun. A few of them repeat, but mostly they don't, so it's a very open game.
Thank you.
Hi. Uy, ¿se me escucha?
Yes, it's working.
Sorry. This is not gonna be a question. It's just thank you, because I'm biologist right now, and I think that you inspire me a lot in high school, because I saw in the books, and I do a lot of works about you and presentations at school, and you're a reference to me, and I wanna to thank you because you inspire me.
Thank you,
thank you.
and I hope you enjoy your science.
Thanks for the talk, was amazing. You mentioned that during the time in which you were a student, you were willing to kind of tick in a report that you met the objectives of for which this funding was given.
Yes.
This is something I also heard from a professor of mine some month ago, that is kind of horrible, that just scientists need to kind of define the outcome before doing the research. What's your take on the evolution of that? How the funding is kind of requested, and this kind of objective met stuff?
So you're talking about somebody starting research?
Yeah. When you ask for a grant,
yeah,
somehow you need to in the document in which you ask for this grant, you already need to define what's gonna be the outcome of this research.
yes.
And this is something that one professor I know was complaining about, and she was quite frustrated about it. And you just mentioning it. And how do you think this has been evolving over the last decades? Whether it's gotten worse or better?
Yeah, it's fairly standard these days that if you apply for money, you have to say why you want the money, what you are going to do with it, and what problem you hope you can solve, what question you can answer. And you have to be very good at writing good cases to get money. Maybe you think you're doing science because you are not good at writing. You are not good with words. Get good with words quickly. You need it, because to get funding, you have to write applications, and they have to be strong and interesting and effective writing. It's very, very important these days. And there's always too many people wanting this much money. If we had that much money, maybe, but it's only this much money, and there might be, I don't know, 5 times oversubscription, 10 times oversubscription. I'm not quite sure what the rates are in different countries. But it means that 1 in 5 or 1 in 10 will get the money and the others will not.
And this kind of ticking the objective met, so knowing what's gonna be the outcome before even starting the work, is it getting any better or any worse? What's your observation on that?
To get money, you have to say, we'll investigate da, 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 and be able to say whether or not quasars have a black hole of 10 to the 6 or 10 to the 4 solar masses inside them. So you've got to be clear that you're going to answer an important question. And just saying, I'm a brilliant astronomer, I've done blah, 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 and I'd like some money, please. I mean, I'm being almost facetious, but you have that open, that loose a case will not get money. You have to be really tight. Having said all that, there is evidence that cases written by men are more often successful than cases written by women. And this is one of the things that is currently being addressed by at least some of the funding bodies. I think maybe the women don't use strong enough words, strong enough adjectives. Equally, when they apply for jobs and you make a case, you need to have some strong verbs. For English speakers, I have a list of strong verbs, but I can't do it in other languages.
Thank you.
Good afternoon, Dr. Bell. I just wanted to ask, and I don't know if that's a bit of a stupid question. I really don't know that much about astrophysics, but as far as I know, if you want to measure a pulsar, its radiation burst should be pointing Earth somehow.
Yes.
Is it possible to measure pulsars who are not pointing Earth whatsoever?
No, we're probably only able to see about 1 in 5, 1 in 10, because you're absolutely right. If this is the pulsar beam, if it comes round like that, you'll all be able to pick it up. But if it comes round like this, none of you will see it. So we reckon about 1 in 5 we could see.
Okay, thank you very much.
Okay, thank you, Jocelyn, again. We hope you are having a good time in Tenerife. And thank you for coming again.
Thank you. Thank you very much.